Let's take a look at what we do with these numbers when we put them to full compounds. So just a little note on terminology. When I have something that is ionically bound, I've got this whole lattice of cations and anions and cations and anions. And so we represent those with that lowest ratio of everything. We put them in terms of formula units. With covalent compounds, we have discrete molecules. And so these terms, we can call ionic compounds the formula mass and covalent compounds the molecular mass. A lot of times this ends up just getting shorthanded into molar mass. I always learn to abbreviate it as just MM. So it means the same thing. We're just talking about the mass of the whole compound itself. So when I look at formulas, I have multiple different types of formulas. Some formulas might just have one of each atom. Other formulas like aspirin, we're going to have 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. When I look at this, I can look at a discrete molecule and just say I have 9 carbon atoms. Now, if I had a whole mole of aspirin, I would have 9 moles of carbon atoms. Okay, so we have to look at our formulas so that we can understand the relationships within those. So we can just, look simply at something like this, where in water, how many atoms of H? Oh, we have 2. How many atoms of oxygen? We have 1. In barium nitrate, we have 1 atom of barium. The nitrate ions in parentheses with 2 of them, which means I have a total of 2 nitrogens. I have 3 oxygens in each nitrate for a total of 2 nitrates, so I have 6 oxygens. Okay, so it's important to be able to look at a formula and figure out how much of each thing is in a formula. Okay, when we look at the mass of an individual element, we call that the atomic mass. And now when we look at the mass of a compound, we call that the molar mass. And so I abbreviate this with MM. And so to get it, all we do is we sum up the masses of the constituent elements. So this one right here, this is carbon dioxide. And so I have 1 carbon, so I would do 12.01. And then I have 2 oxygen, so I do 2 times 16.00. And that's where we get the 44.01. Okay? We can say that's 44.01 AMU, or as we learned, we can call that 44.01 grams per mole. Okay? We have all sorts of different substances, all with different masses, and so when we think about 1 mole of a substance, everything's going to have a different amount in that 1 mole because everything has a different mass. Nitrogen, it's a gas, it expands, it's super light, and so it takes a lot of it to get to 28 grams of it. Mercury, super dense, it's a liquid, we don't need a whole lot of it for 1 mole. So this image illustrates what 1 mole of each of these substances looks like. So you can see it's vastly different. Here's another one that just shows a whole bunch of different substances. There's some straight substances, there's some hydrates there, and so this is what 1 mole of each of these substances look like. And so when we calculate those masses, again, we just simply sum up the individual pieces and we get the molar mass of that particular compound. All right, so let's try an example. All right, so we have nitric acid. We want to know how many atoms of oxygen are in a sample of nitric acid. So we're starting with grams of nitric acid. And we need to get 2 atoms of oxygen. Okay? So how do we do this? Well, we know that we have a different number of grams and everything. So we have to go through moles. So we can go from grams of nitric acid to moles of nitric acid. Okay, we can use the molar ratio inside of our formula and go from moles of nitric acid to moles of oxygen, and then we can go from moles of oxygen to atoms of oxygen. And so for grams to moles, we need the molar mass. To go from moles to moles, we need the ratio of each element in our compound, and then we need to go from moles to atoms, so we need our Avogadro's number. So we'll calculate the molar mass. I'll do that up here. So I have HNO3. So hydrogen is 1.008, nitrogen is 14.01, and then I have 3 oxygens, each at 16. So my molar mass of nitric acid is going to be 63.018 grams per mole. Okay? So we'll take our 28.5 grams nitric acid times 1 mole for every 63.018 grams. Okay, now in my formula I have 3 oxygens, so we say that we have 3 moles of oxygen for every 1 mole of our nitric acid. And then we have our Avogadro's number, where I have 6.022 times 10 to the 23rd atoms of oxygen and every 1 mole of oxygen. Okay? And so we end up with 8.17 times 10 to the 23rd atoms of oxygen. Okay, and we have 3 significant figures because up here I have 3 significant figures for my measured value. And so that's why I rounded that to 3 significant figures. Okay. All right, let's try another one. Okay, we have hydrogen cyanide. So we have number of molecules. We want to know the mass. So we're going from molecules of hydrogen cyanide to grams of hydrogen cyanide. Okay? So when we think about our full roadmap here, I can't go directly from molecules to grams. I have Avogadro's number, which is entities per mole. I have a molar mass, which is grams per mole. So again, the commonality there is moles. So we're going to go from molecules to moles and then to grams. Okay, in order to do that, we do need to know the molar mass. So I'll calculate that up here. Okay, so hydrogen is 1.008, carbon is 12.01, and nitrogen is 14.01. Okay, so you can absolutely look at a periodic table as you do this. I have a lot of these memorized because I've worked with them for a very long time now. So you might find that as you work with something and you do something a whole bunch of times, you start memorizing something without even thinking about it. So I have a lot of the masses memorized just because I use them all the time. But I have a lot of them I have to look up still too because I don't use them as much. All right, so we end up with 27.028 grams per mole. All right, so we can do our 3.14 times 10 to the 19th molecules of hydrogen cyanide times 1 mole of hydrogen cyanide in our 6.022 times 10 to the 23rd molecules of hydrogen cyanide. And then we have 27.028 grams for every 1 mole. Okay, and we get 1.41 times 10 to the negative third grams of hydrogen cyanide. So not a whole lot, just a tiny little bit. Okay, let's try some more. We're going to do methane over the next little bit here. So our first thing asks us to calculate the molar mass of methane. So instead of giving you the formula, I put a couple of pictures up on here. So if I look over here, I have this. Well, if I look at this, how many carbons do I have? I have 1. And how many hydrogens do I have? I have 4. So methane is CH4. So to get the molar mass, we're going to do 12.01 for our carbon plus 4 times 1.008 for our hydrogen. And we're going to get 16.042 grams per mole. Okay, so now we need number of moles of carbon and 3.54 moles of methane. So I take 3.54 moles. Okay, and then when I look at my formula, I have 1 mole of carbon for every 1 mole of methane. And so I get 3.54 moles of carbon. Okay. All right, now we can do that for hydrogen. So I have 3.54 moles of methane still, but how many moles of hydrogen is that? Okay, well, according to my formula, I have 4 moles of hydrogen for every 1 mole of methane. So this time, I'm going to get 14.16 moles of hydrogen. Second. Okay, and we have 3 significant figures, so I'll cut it there. So I'm going to get 14.2 moles of hydrogen. Okay, let's keep working with methane. If you pulled my slides, this is all on one slide. I split it into 2 slides for the lecture because I have to have space to write, and I was able to squeeze it all in on my normal handwriting, but you wouldn't have been able to read it if I'd had it all squished on here. So we're going to keep working with this. All right, now I have grams of methane. Okay, I want to know moles of methane. So this is where we need that molar mass that we calculated a moment ago. Okay, so we're going to go from grams to moles. In order to do that, we need that molar mass. Okay, so we're going to take 0.29 grams of methane times 1 mole of methane in our 16.042 grams of methane. Okay, and we should get 0.205 moles of methane. Okay? All right, now we're going to go from moles to grams. Again, we need the molar mass for that, so we'll take our 2.54 moles. We have 16.042 grams in every 1 mole. Okay, and so we get 40.7 grams. Okay. All right, let's do one more compound. All right, so I've got some lead 2 chromate. I put a picture. It's this bright yellow color, so it looks really cool. It's known as chrome yellow because the yellow color is coming from the chromium that is in there. All right, so let's do our molar mass. Okay, so lead, this is one I even have to look up because I don't use it that often. But lead is 207.2. Okay, chromium is 52. And then oxygen is 16, and there's 4 of them. All right, we are going to get 323.2 grams per mole. Okay, so this says if you precipitate a certain number of grams of lead-2 chromate, how many moles do you precipitate? So when we precipitate something, if I have a reaction and I mix 2 things together and I have a solid that comes out of solution when I mix those 2 things together, that solid is called a precipitate. And so if I am trying to make this by mixing things together and I precipitate out, that is my solid lead-2 chromate. All right. So we're going to go from grams to moles. So we just need the molar mass. So I have 45.6 grams of lead-2 chromate. I have 1 mole in every 323.2 grams. And we end up getting 0.141. Okay, all right, so now we're going to keep using the same sample. So if you notice, my next question just says how many formula units of lead-2 chromate precipitate. I didn't give another number. So this is what we're working with the whole time. Now, for this next one, I could start at the grams, and I can do grams to moles, and then moles to my formula units. If I do it that way and I do it all on my calculator, what I save is a little bit of a rounding error. Because each time you stop, write an answer down, round off, and move on, you can end up with rounding errors. But we've already calculated the moles, so we're just going to go ahead and go with that. So we just calculated that we had 0.141 moles, and we know we can go directly from moles to formula units with Avogadro's number. So I'm going to do my 0.141 moles times 6.022 times 10 to the 23rd units in 1 mole. Okay, and we're going to get 8.49 times 10 to the 22nd units. Okay, now it asks just for moles of lead. So now we're going to use the molar ratio within our compound itself. So we're going to get 0.141 moles of lead-2 chromate still. I have 1 lead, so I have 1 mole of lead for every 1 mole of lead-2 chromate. So I have 0.141 moles of lead. Okay. All right. Now I want to know how many atoms of lead were in that sample. Well, we just calculated the moles of lead, right? So can I go from moles of lead to atoms of lead? Yeah, with Avogadro's number. So I take my 0.141 moles of lead times 6.022 times 10 to the 23rd atoms of lead in 1 mole of lead. And I get 8.49 times 10 to the 22nd atoms of lead. Okay, we're going to do the same thing for oxygen. We'll figure out atoms and moles. So first moles, because if I know moles of lead-2 chromate, I can easily figure out moles of oxygen. So I had 0.141 moles of my lead-2 chromate. Okay, now according to my formula, I have 4 moles of oxygen for every 1 mole of lead-2 chromate. So I get 0.564 moles of oxygen. All right, and now I can go to atoms. I can take my 0.564 moles of oxygen times 6.022 times 10 to the 23rd atoms in 1 mole. And I'm going to get 3.39 times 10 to the 23rd atoms of oxygen. Okay, so I'm going to stress again, practice. You got to practice these. This takes, a decent amount of time to really get comfortable with the progression that all of these go in. So make sure you do practice.